Now that we understand what it is that we need to do to analyze electromagnetic circuits, let's develop some of the mathematical and analysis techniques that are actually going to get us some useful answers. And we're going to start that by just looking at a conventional circuit that we would analyze with circuit analysis techniques. So this circuit that I'm showing in figure A here. In conventional electronic circuits, the wire that connects a source to a load, so this, what we would call a wire connecting from here to here, is assumed to be ideal. And by ideal, we mean that they have the following properties: that the resistance of this wire is 0 ohms, the inductance of the wire is 0 henries, and the capacitance of the wire is 0 farads. This assumption, what it mathematically leads to, is that a signal generated by this voltage source is going to appear instantaneously at this load, and there's not going to be any phase shift between the voltage at the signal source and the voltage at the load, assuming that this is a resistive load only. So for example, let's consider a 100 volt DC battery with a switch that closes at time t equals 0. And we've got some sort of transmission line that connects us to a 50 ohm load. So again, 100 volts, 50 ohms. What conventional circuit analysis would tell us is that I is equal to the voltage divided by R, and that's just 100 volts divided by 50 ohms equals 2 amps. So we've got some length of wire, and conventional circuit analysis would lead us to believe that 2 amps appears instantaneously in the entire circuit because of the drop of 100 volts across the 50 ohm resistor. However, this is not true. In reality, a voltage and current waveform is going to propagate along the transmission line from the source down to the load, and eventually the current value will reach 2 amps. Eventually. But this takes some finite period of time, and in the very, very short term, the current value anywhere in the wire can be less than 2 amps. It could actually be more than 2 amps. And the actual value of the current at any given time will depend on the constructive and destructive interference of the incident wave and then what's called a reflected wave. So as those two waves add together, the actual value of the current will be the summation of those two waves. To analyze such circuits, we will typically start with a circuit model that we call a transmission line, which is really just a wire that we develop to have a realistic circuit model. By developing the circuit model, we're going to begin to analyze why delay occurs in wires, and we will use transmission line models whenever the length of wire connecting a source to a load is a significant fraction of the signal's wavelength. And so down here I show some of the ramifications of actually using a transmission line. We've got a source. It is putting out a voltage at angle 0. The voltage is sent to a purely resistive load through a transmission line, and we see that there can be some phase shift. I don't mean to imply that there's always 90 degrees of phase shift. We will just say that there's VR at an angle of theta, meaning that there is a difference between the voltage angle here and the voltage angle there. So, and I'm showing, if you aren't really familiar with phase shift, here's an example of what phase shift may look like. This is for the specific case of 90 degrees of phase shift. We see that the source leads the load by 90 degrees, or pi over 2. So what I want to show next is how an ideal pair of wires can be transformed into a transmission line. So typically we have a source. We'll represent that as a 2-port network. And then we have a load, which we'll also represent as a 2-port network. And the transmission line is just the length of wire that connects the source to the load. In basic circuit theory, the voltage at all points along this wire is going to be exactly the same. However, real wires are going to have a series resistance associated with them. They're also going to have a series inductance associated with them. So we've got a series resistance and a series inductance. And additionally, wires are going to have a capacitance between two wires. So between the supply and the return, there's a capacitance that develops between those wires. And since there's no such thing as a perfect insulator, any wire is going to have a leakage current associated with it, meaning that not all the current is going to flow this direction. There's some of the current is going to leak out through the insulator, whether that's insulators, air, polyethylene, or whatever. And we indicate that as a shunt resistance. So we've got, in real wires, we've got an R, we've got an L, we've got a C, and we've got another R, where that is resistance, that's inductance, that's capacitance, and that's R, resistance. We typically don't use R there. We talk about how much current flows, and so instead we use conductance as that measured. So that's a high value shunt resistor there. So this is the basic transmission line model. We've replaced a wire with a RLC R circuit, and sometimes we'll use this model, which is pretty realistic. Other times we will eliminate the resistance and the conductance, and we'll just look at the circuit such as containing a inductance and a capacitance. So we get a load, and we've got just an inductor and a capacitor. This is called the transmission line model. This is called the lossless transmission line model. So this is maybe sometimes better called lossy, and this is called lossless, where lossless is just a simplification of the lossy model. The effect of eliminating those resistors is that no real power is dissipated in the transmission line. Therefore, if power is dissipated, we call it lossy. If no power is dissipated, we call it lossless. You should be aware that all transmission lines are in reality lossy. A lot of times we just use the lossless model to make our math that we'll use later a little bit easier. So while this model is an improvement over the ideal assumptions, it's still not the best model. The primary problem with it is that all the resistance of this wire here is lumped into a single element, and all the inductance of this wire here is lumped into a single element. Then the same for the capacitance and the conductance as well. In reality, these properties are distributed along the entire length. You know, the resistance doesn't exist just here. It's actually spread out over the entire length of the wire. So one way to fix this would be to create a transmission line that has a bunch of elements in it. So I'm going to use the lossless transmission line and say we have a DC input. So a better way might be that we take the L value from here and we put another inductor there that's L over 4. And we take the C value that's here and we put a capacitor that's C over 4. And of course, to get this total value, we know that inductors combine in series, so we would have to take L over 4, L over 4, C over 4, L over 4, C over 4, L over 4, and I think you get the picture. A final C over 4. So this might be a better model. In reality, it would be best to model the transmission line as an infinite series, of infinitesimally small inductors and capacitors. So the best idea would be, can we just make this a delta L here, an extremely small value? And we'll do that later in the class, but for now what I want to focus on is what happens to a signal going from here to here if we use some sort of transmission line that's got this L over 4 distributed architecture as we have here. So before the battery is connected to the circuit, if there was a switch here and this was open, before the battery is connected to the circuit, there's no voltage on the line, there's no voltage on whatever load we have connected to this transmission line over here. There's no current flowing either. Immediately after the switch is closed, current is going to flow from the battery into the transmission line. However, it isn't going to immediately reach the load. Instead, the current is going to flow through this inductor and it's going to be diverted by this first capacitor. The capacitor sinks the charge, and the capacitor is going to continue to sink that current until it is the same voltage as the battery is right here. During this process, some energy is also transferred to the magnetic field of the inductor. As the voltage on this capacitor starts to climb, some of the charge is going to trickle into the second stage here. This process is going to continue until each of the capacitors is fully charged to the battery voltage, right here. Only after each of the capacitors is fully charged is the voltage of the battery going to appear across the load terminals. Only then will the load resistance see the full battery voltage. During the charging of the capacitors and inductors, no current's going to reach the load either, since the charge is being diverted into each of these little capacitors. The battery itself, therefore, doesn't even know that it's connected to a load resistor. All it can see is the value of the inductors and the capacitors that are charging. This impedance that the battery is seeing, it's called the characteristic impedance of the transmission line, and it's given the symbol Z0. And again, we call that the characteristic impedance. And for a lossless transmission line, the calculation for the characteristic impedance is very simple. It's Z0 equals the square root of the total L divided by the total C. And that's for a lossless. And a similar analysis, if we had included R's in the series and the shunt paths, we would have found that Z0 is equal to the square root of R plus J omega L over G plus J omega C, and this is for a lossy T-line, so a more realistic T-line. The capacitance and the inductance that we used in this lossless transmission line model are actually a consequence of the material properties and the geometry of the conductor. The capacitance is related to the electric permittivity of the material, and the inductance is related to the magnetic permeability of the material. And therefore, capacitance and inductance can also directly be related to the propagation velocity of the wave. And the relationship there is that the propagation velocity of the wave is equal to 1 divided by the square root of the product of the inductance and the capacitance for both a lossy line and a lossless line. That holds true, whichever of these two models we happen to be using. Later in the course, I'm going to more rigorously develop the formula for characteristic impedance of both the lossy and the lossless transmission line. For now, the important thing to remember is that the characteristic impedance Z0 of a transmission line is the impedance of the line as experienced by the battery or other source while the signal is moving down the transmission line. So characteristic impedance is what does this battery know about the signal before the line has become fully charged. Older engineers, if you're working out in industry, a lot of times called this surge impedance. And this is because that if the source is a DC battery, as we've shown in this example, to the battery, while the signal is moving down the transmission line, a constant current draw is seen from the source, and so the transmission line looks like a resistor. It's the current being drawn into these capacitors. So there's a constant current draw that isn't actually related to the load. Once the signal has reached steady state and all these little capacitors have been charged, the battery no longer sees this impedance and the surge has ended. The characteristic impedance of a transmission line is a very real effect. This isn't just some sort of mathematical textbooky parameter. And for example, imagine that you were to build a very long coax cable and we stretched it from the Earth to the Moon to connect to a 1 kiloohm load. The typical characteristic impedance Z0 of a coax cable is 50 ohms. If you were to connect an ohm meter to the cable, it would initially read 50 ohms, not 1K, which would be connected to the end on the Moon. After about 4 seconds, after the T-line capacitance and inductances had fully charged and all resonant oscillations had died out, then only will the meter read 1K. In contrast, a 1 meter cable would only take a few nanoseconds to charge, and for this reason, it's often inconsequential to low frequency analysis.